Students, our next topic is continuous charge distribution. So, as the name suggests, the charges are distributed or spread uh, over an area continuously. So, basically, in general practice, we ignore the quantum nature, that is, the minute size of the charges, and imagine that the charge is spread in a region in a continuous manner. So quantum nature is that the charges exist in discrete packets, but we imagine that or we consider the charges are in a continuous manner. They are spreading over or they are moving in a continuous manner. So such a charge distribution is known as continuous charge distribution. So here we are having an area, and this is the total charge Q is spread over this area. Let us consider a small charge of this distribution, and a test charge is placed at a distance r vector from this small charge. Now, according to Coulomb's law, the force experienced by this test charge due to charge dq is given by, that is the small amount of force, df vector is equals to 1 upon 4 pi epsilon naught q naught, the given charge, dq is the source charge and the separation between the two charges, with the unit vector that shows the direction of force acting on this test charge. So this unit vector is pointing from this dq to q naught. By principle of superposition, the total charge on q naught due to all the small charges is, that is the total force F vector, will be the integration or the combined effect of all the forces due to all dq charges is equals to integration of df, that is equals to integration of 1 upon 4 pi epsilon naught q naught dq upon r square, r unit vector, where this q naught charge remains constant, 1 upon 4 pi epsilon naught remains constant. Hence, the net forces F vector is equals to q naught upon 4 pi epsilon naught integration dq upon r square and unit vector. There are three different types of continuous charge distribution: volume charge distribution, surface charge distribution, and the linear charge distribution. First of all, let us study the volume charge distribution. As the name suggests, the charge is distributed over a volume, that is a three-dimensional object. So this is our three-dimensional object with volume V, and the positive charge is distributed over this volume. Consider a small charge distribution, that is dq, of this whole distribution, and there is a test charge which is experiencing the field due to this small charge dq, which is at a distance r from this dq. dq is equals to rho dv, where rho is the volume charge density. So this volume charge density at a point in a given volume is defined as the charge contained per unit volume at that point, that is rho is equals to dq upon dv. Mark it as equation number 1. If q is the charge distributed over the volume, that is q is the total charge over the volume V, then rho is equals to q upon V, is equals to Q upon 4 by 3 pi r cube, where 4 by 3 pi r cube is volume of the sphere and the unit is coulomb per meter cube. Now, the charge contained in small volume dV, that is dq, is equals to rho dV. Therefore, the total electrostatic force on volume V due to the charge Q naught is given by Fv, that is force on volume, is equals to Q naught upon 4 pi epsilon naught. This is constant quantity, and the volume integration of dq upon r square, r unit vector. This is equals to Q naught upon 4 pi epsilon naught volume integral rho upon r square dv r vector. Hence, the electric field due to volume charge distribution at the location of charge Q naught is volume, electric field over volume is Fv upon Q naught, and that is equals to 1 upon 4 pi epsilon naught volume integration rho upon r square dv unit vector r. So students, after the volume charge distribution, next is surface charge distribution. It is charge distributed over a two-dimensional surface S in space. The SI unit for sigma is coulomb per meter square. So here we are having an area over which the positive charge Q is uniformly distributed. Let us consider a small area ds of this configuration over which dq charge is being distributed, where dq is equals to sigma ds. Sigma is surface charge density. A test charge Q naught is placed at distance r vector from this area ds. So, the surface charge density at a point is defined as charge per unit area at that point. Hence, for a spherical conductor, sigma is equals to charge upon the area, and we know that area for this spherical sphere is 4 pi r square, and the unit is coulomb per meter square. The charge contained in small area ds is dq is equals to sigma ds. Therefore, the total electrostatic force exerted on charge Q naught due to the entire surface is given by F, force over the surface, is equals to Q naught upon 4 pi epsilon naught integration over the surface sigma upon r square ds unit vector r, and hence the field is given by field is force upon the charge, and that is equals to 1 upon 4 pi epsilon naught integration over the surface sigma upon r square ds unit vector r. Similarly, we can easily find out the linear charge distribution in which the whole charge is spread over the line. Consider the small length dl. Again, the test charge at distance r unit vector, and the small charge for this length is lambda dl, where lambda is linear charge density, that is the charge per unit length. So, the electric field due to line charge distribution is given by EL vector is equals to FL vector divided by Q naught is equals to 1 upon 4 pi epsilon naught integration over the line lambda upon r square dl unit vector r. So students, our next topic in electrostatic is electric dipole. As the name suggests, electric means charges, di means two, and pole means polarity or opposite charges. So an electric dipole is a pair of equal and opposite charges separated by a small distance. A dipole moment for a given dipole is defined as the dipole moment of an electric dipole is a vector whose magnitude is either charge times, that is, the magnitude of either charge and the separation between the two opposite charges. And the direction is along the dipole axis from the negative to the positive charge. So here we are having one negative charge minus q, another positive charge plus q, separated by distance 2a. So this is the condition for a dipole, that the magnitude of two charges should be equal and the polarity should be opposite, that is, one should be minus, another should be the positive charge. Hence, the dipole moment for a given dipole is defined as the magnitude of charge and the separation between the two charges. This dipole moment is a vector quantity, hence its magnitude is P is equals to Q into 2A, that is, dipole moment is equals to charge into the separation. Now this electric dipole concept is already present in our nature, that is, if we consider the hydrogen molecule, they exist in dipole. One is positive, another one is negative. Similarly, for HCl molecule, the hydrogen is positive and the chlorine molecule is negative. Hence, they exist in dipole. Now, what is the dipole field? Like for a given charge, we are having the field or the area where we can experience the influence of that charge. Similarly, the dipole field is produced by an electric dipole. And point to remember that total charge on dipole is 0, but the electric field of an electric dipole is not 0 because of the separation between the charges. Hence, we are having minus q plus q. The resultant of these charges is 0, but there is net resultant electric field for this dipole. Now, let us find out the electric field at an axial point of a dipole. Axial means along the axis. So students, we are having a dipole, that is charge minus q, charge plus q, separated by distance 2q. O is the center point of this dipole and P vector is the dipole moment for this given dipole. Let us consider a point P where we need to find out the electric field due to this dipole. This point P is at distance r from the center of the dipole. At this point P, there are two electric fields acting. E minus Q is field because of charge minus Q acting towards left side, that is towards minus Q charge, and another electric field E plus Q due to charge plus Q and acting towards right, that is along plus Q. So the electric field due to charge minus Q at point P, E minus Q vector is equals to minus Q divided by 4 pi epsilon naught R plus A whole square P unit vector acting towards left, that is minus Q, and vector P is from charge minus Q to charge plus Q. Similarly, the electric field due to charge plus Q at point P is plus Q upon 4 pi epsilon naught R minus A whole square P vector acting towards right side. Now here the separation of this charge plus Q from P is total distance R minus O plus Q distance. So this is R minus A. We are taking it as R minus A. But in previous case, it was R plus A. Now, in order to find out the net resultant electric field, let us add these two fields. So, the total electric field along the axial point is E plus Q plus E minus Q. Q upon 4 pi epsilon naught is common, and adding the remaining terms, taking the LCM and solving the terms, we are getting E axial is equals to Q upon 4 pi epsilon naught 4AR upon R square minus A square whole square. As we know that P is equals to Q into 2A, that is the dipole moment. After substituting, we are getting the net electric field as 1 upon 4 pi epsilon naught 2 P R square minus A square square and P vector. For the distance R much greater than the separations between the charges, then we can neglect A square, and hence the net electric field along axial line is 1 upon 4 pi epsilon naught 2p by r cube p unit vector acting towards right. Next topic is the electric field at an equatorial point of a dipole. Again, we are considering a dipole, that is minus q charge at point A plus q charge at point B, separated by the distance 2a, A plus A. O is the center point and P is any point on the perpendicular passing through the center. So this is the equatorial point which is on a line perpendicular passing through the center of the dipole. This AP is making an angle theta with the dipole. Similarly, BP is making angle theta with the dipole. OP is equals to R. Now, because of charges minus Q and plus Q, electric fields are acting at point P. So, due to charge minus Q, the field is along PA towards the negative charge, and due to plus charge, the field at point P is along the direction BP, that is the positive charge, away from the positive. Now, the electric field at P due to charge plus Q is given by E plus Q vector is equals to 1 upon 4 pi epsilon naught q upon r square plus a square. That is the separation between the two. Now, here this PB is equals to r square plus a square under root. By applying the Pythagoras theorem for this right angle triangle POB. So this is the hypotenuse, perpendicular and the base. Now similarly for the charge minus q, the field E minus q vector is given by 1 upon 4 pi epsilon naught q upon the separation square. Now the separation is under root. So taking the square, we are getting r square plus a square acting along PA. Hence, the magnitude of E plus Q and E minus Q are equal. So, we can say that E plus Q is equals to E minus Q is equals to 1 upon 4 pi epsilon naught Q divided by R square plus A square. Therefore, the total electric field is given by E equatorial is equals to the perpendicular component, the horizontal component for the charge minus q plus the perpendicular and the horizontal components for the charge plus q. As the perpendicular components, the electric field perpendicular to the dipole is equal and opposite. Hence, they are getting cancelled out and the net resultant field along this is due to the parallel component, that is the cos factor. So, the net equatorial electric field is minus EQ cos theta plus E plus Q cos theta and is equals to minus 2 EQ because the magnitudes are same cos theta P unit vector. Substituting the value of this electric field, we are getting the net electric field as minus 2 1 upon 4 pi epsilon naught Q divided by R square plus A square into A upon under root R square plus A square. This is the value of cos theta from the given figure. Hence, the net equatorial electric field is given by minus 1 upon 4 pi epsilon naught P divided by R square plus A square whole power 3 by 2 P unit vector. For the distance R greater than A, the net equatorial field is given by 1 upon 4 pi epsilon naught P upon R cube unit vector. Now, why we are considering this negative sign over here? Because the dipole direction is from negative to positive charge along this direction, but the net resultant electric field along equatorial is opposite to the direction of the dipole. Hence, we are considering the negative sign over here. After the dipole, our next topic is torque on a given dipole. That is torque on a dipole in uniform electric field. We are considering a dipole minus q plus q. Separation is 2a. In a given electric field, these are the field lines showing the electric field E. Now, because of this electric field and charge magnitude, a force minus QE is acting on this negative charge along the left side, and similarly a force plus QE is acting on this plus Q charge towards the right. This dipole is making an angle theta with the electric field, and 2a sine theta is the perpendicular distance of this dipole by applying the Pythagoras theorem. Now, in the simplified form, the field is along this direction, dipole moment is along this direction, making an angle theta with the electric field. And because the force is acting on the charges, so they are tending this dipole towards the downward direction. Hence, a torque is acting on this dipole, and the magnitude of torque is P into E. You had already studied in your 11th class that torque is equals to force into the perpendicular distance. Now, the formula for dipole is P is equals to Q into 2A, and the force on charge minus Q by the field E is equals to minus QE, opposite to the direction of the electric field, and force on charge plus Q by the field E is equals to QE, and this force is along the direction of electric field. So the total force acting on the dipole is plus QE minus QE, that is equals to 0. That is, the net resultant force acting on the dipole is 0. But the two equal and opposite forces act at different points of the dipole. Hence, they form a couple which exerts a torque on this dipole. So they are exerting a couple, and that is rotating this dipole in this manner. So the torque is acting on this dipole because of the couple created. Therefore, the torque is either force magnitude into the perpendicular distance between the forces. So torque is force magnitude is QE, and the perpendicular distance is 2A sine theta is equals to Q into 2A E sine theta, where this is the dipole moment. So therefore, torque is PE sine theta. In vector form, torque vector tau is equals to P vector into E vector. From this equation, there are special cases like when the theta is 0 degree, that is, the dipole is along the electric field. In that case, the torque acting is 0 because sine theta, sine 0 is 0. Similarly, for theta is equals to 180 degree, again the torque is minimum, that is 0. But for theta is equals to 90 degree, the torque acting is PE sine 90, and that is P into E. That is the maximum torque acting on this dipole. Students, now let us solve numerical problems based on the electric dipole. So the first numerical is two charges, one is of plus 5 microcoulomb and other minus 5 microcoulomb, are placed 1 millimeter apart. Calculate the dipole moment. So here the given quantities are charge is 5 microcoulomb, that is 5 into 10 raised to power minus 6 coulomb, and the separation is 1 millimeter is equals to 10 raised to power minus 3 meter. Therefore, applying the formula for the dipole moment, that is P is equals to 2QA is equals to this. After substituting the values, we are getting the dipole moment for the given dipole is 5 into 10 raised to power minus 9 coulomb meter. That is the unit for the dipole moment, charge into distance. Next numerical problem is an electric dipole consists of two opposite charges of magnitude 1 by 3 into 10 raised to power minus 7 coulomb separated by 2 centimeter. The dipole is placed in an external field of 3 into 10 raised to power 7 Newton per coulomb. What maximum torque does the electric field exert on the dipole? Here, the given quantities are Q, that is, the charge is 1 by 3 into 10 raised to power minus 7 coulomb. Separation is 2 centimeter, that is 0.02 meter, or 2 into 10 raised to power minus 2 meter. The field is given 3 into 10 raised to power 7 Newton per coulomb. Applying the formula of torque, torque is Pe sine theta. For maximum torque, theta is 90°. Therefore, maximum torque exerted on the dipole is Q into 2A E into 1, that is sine 90 is 1. Substituting the values of the quantities, maximum torque comes out to be 0.02 Newton meter. Students, here is one numerical problem for your practice. An electric dipole is formed by charges plus 4 microcoulomb and minus 4 microcoulomb at 5 millimeter apart distance. Calculate the dipole moment and give its direction. So the charges are given, distance is given. Apply the formula for dipole moment, that is P is equals to Q into 2A. Substituting the values and you will get the result for this numerical problem.